Today's lecture is about neural networks, and the agenda of this topic is first, we'll try to give you some motivation why exactly neural networks are required. And in that aspect, we'll try to cover two different aspects. The first is feature engineering, and the second is feature learning. So we will see that some part of feature engineering we have already covered, like the basics, and neural network is kind of basics for feature learning. So we'll try to connect these two concepts and how these are different and how they're trying to solve actually the same problem. Then we'll try to cover some of the basics of neural networks, or what exactly these neural networks are and how we can actually use them. And then there is a very interesting concept of non-linearity, which is actually used in neural networks, not just neural networks, like any kind of network you have. So we'll briefly talk about that. So let's start with the first topic, which is feature engineering versus feature learning. Now, so far in the course, we have seen given an input image, we can detect edges. Okay, so that's just the beginning. And of course, if the end goal is to actually detect edges, I mean, your problem is solved. But usually, like in real world applications, you ideally want more than that, not just detect edges. Okay, so the question is like, okay, once we have detected these edges, where we can go from here? In the previous lectures, we have been talking about filtering. We have studied like how gradients can be used to detect these edges. We try to cover different algorithms to detect edges. So the next step is, once we have these edges, can we extract some meaningful features? And by meaningful features, I mean some kind of conceptual representation of your input image, okay, which will make your task easier. Let's say if you're doing image classification, so these features will help you out. Okay, so for example, like if you're doing image recognition, or it could be scene recognition, place recognition, like there are a lot of other variations, then these features will be very, very useful. And again, if you're doing object detection or action detection or any other detection task, again, these features will be useful. It could be segmentation. So whatever variation of computer vision problem you have in your application, you will need these features. Now, let's try to understand, like at a high level, when we're trying to do object classification, what exactly is happening under the hood. So for example, if this is your image, and let's say you have to classify your set of images as whether these are motorcycles or not. So what you'll have to do is your input will be this image. Then you'll have some kind of model. You can say, let's say machine learning model, which is going to tell you whether this is motorcycle or not. Okay, so this is like a very basic image classification problem. Now, the problem with these kind of models, and we have seen this before as well. So visually, we can see like it's a motorcycle, and it's very easy for us to make like these kind of interpretations. But as we discussed earlier, like in images, when computer tries to seize these images, if you focus on this patch, the camera or the computer, whatever your algorithm is, it's just seeing this bunch of numbers. And even for us, like as humans, I mean, these numbers, I mean, it's very hard to interpret. There is no way of saying that, okay, these numbers are actually coming from motorcycle or not. Okay, so that's the difficulty. So now let's try to understand how we can resolve this. And we have partially covered this aspect in one of the previous lecture as well. So what's the very basic thing we could do? If we have this input image, we can represent this image at pixel level. All right, so pixel level means for each pixel, you have 3 different values if it's RGB image. And you can say that, okay, this pixel has red color, this pixel has green color. So that's like one very crude form of image representation. And you can, in fact, create your algorithm just using that representation. But let's see what are the issues. So let's say we just pick like 2 pixels and we say that, okay, this is like x-axis is pixel 1 and y-axis is pixel 2. And let's say we try to project like the value of that pixel on this axis and also on this axis. And let's try to simplify. Let's say it's not RGB, it's just grayscale. So grayscale, it's easier because RGB, it's already 3-dimensional, right? If we have to project it, it becomes a little bit complicated. So let's say it's a grayscale image, and this this x-axis is representing the intensity of that pixel. So you know that in a grayscale image, pixel value could be between 0 to 255. And this x-axis over here, it's marking like what's the intensity of that pixel. For example, like this, one of the pixel of the motorcycle, let's say it's at this point, and the y-axis is intensity of pixel 2. So this is just showing 2 pixels. But if in your input image, let's say you have 1,000 of pixels, then you will have 1,000 of different dimensions. And you can again just generalize this idea from 2 pixels to a lot of pixels. So this will be your first pixel, depending upon what's the intensity of this pixel. And again, this is like another pixel coming from your image. So these two are like motorcycles. And these are some other images, which are, you can say, negative images. These are not motorcycles. And for the same set of pixels, the values of pixel intensity actually falls at this point for this image, and at this point for this image. And we can try to plot like more such images. And what will happen is your these blue dots here, or the blue crosses, these belong to motorcycles, and the negative red are kind of non-motorcycles, negative motorcycles, negative images, right? So this is kind of your distribution. But if you will see, like, there is no way of knowing like which of these marks are actually motorcycle and which are not motorcycle. So you can't actually draw a very simple boundary which can divide these two. So that's the difficulty of pixel, and that's actually true as well, because your pixel color will change depending upon like the orientation, the lighting condition, a lot of different factors there. So clearly pixel-based representation is not good. Okay, so how can we improve this? So one simple step could be, you can have feature representation, which is actually looking at parts of these images or parts of these objects. Okay, so parts could be, for example, you're looking at, let's say, handlebars, or you could be looking at wheels. And so right now, don't worry about how to actually extract wheels or how to extract handlebars, but just try to understand, like, we are moving from pixel level to concept level. Okay, so let's say our feature representation is focusing on these concepts. And now what we can do is, instead of the axis representing each pixel, these x's are actually representing these concepts. And now let's say x-axis is saying handlebar and y-axis is saying wheels. Then if you try to plot like different images, then what will happen is your images from motorbikes, you will see like they will have handlebars and they will have wheels. So they will fall over here. And then all the negative images, they won't have handlebars and they won't have wheels. Okay, you might have cars as well. In that case, your wheels will go way up, right? Because they might have 4 or more wheels here. And again, they won't have handlebars, so they might lie around this region somewhere. But again, you will be able to differentiate those images of cars or four-wheelers with your motorcycles. So in this case, if you have such a plot, and again, this is just two-dimensional, just two concepts, you might have like a lot of other concepts. It will be like n-dimensional space. But the good thing here is, if you just draw a line over here, then what you can say is, during test time, if I give you an image, depending upon like where that image lies, whether it's like towards this direction or this direction, you will be able to say this is a motorbike or not. Okay, so this is kind of a fine distribution, which is discriminating, or which is helping you in discriminating between these two type of images. Now the question is, how do we get these feature representations? And like before deep learning, or you can say like this data-driven approaches, there were a lot of local features which were developed. And these local features, the whole motivation was to actually try to represent these different concepts automatically. And once you have these features, you can use them to classify different images or to discriminate different images from each other. Okay, so SIFT is one such algorithm. And I think we have a lecture, a complete lecture to talk about the SIFT features. We have spin images, we have HOG features, and there are a lot of others. So this is just a small list, because earlier, like this is like classical computer vision. So everyone was trying to come up with these set of classical features. So it's not just like these 9. You will find like a lot of variations just for these set of features as well. So in the course, I think we are not going to cover all of those because again, it will take a lot of time. But we'll just try to cover some representative which are actually very useful, which were performing very good and are still used today. One of such features are like SIF features and HOG features. So we'll try to cover these two. And the rest, I think, yeah, these we are not going to cover. Now, the challenge with these type of algorithms was these were like kind of handcrafted features. You'll have to think about like how to extract features like manually, and you need expert knowledge for that. And that's a challenge, because whatever feature you can derive using these algorithms, that is limited by whatever knowledge you have. Okay. So that has changed a lot. And I'm not saying these features are bad. These features still have like some very nice properties, and people haven't started looking back to like these features, but we have some like ongoing research where we have seen that if we try to integrate like these local features with like the deep learning paradigm, we can like do something much, much better than deep learning. And I won't talk like a lot about this because that's like an ongoing research, but just to give you an idea. Okay, so those local features, it was all feature engineering, which means you need some kind of domain expertise or some kind of domain knowledge to come up and design these features. Now, these days, like with deep learning, it has converted to feature learning. Okay, so we are not engineering these features in any way. All we are doing is we are trying to learn these features. Okay, and how these features will be learned. Half of this course is actually just focusing on that. And the neural network, the lecture we'll discuss today, it will start with like neural networks. That's kind of a basic building block of how these features can be learned. Okay, so the feature engineering, as I said, you need some kind of expert knowledge. And for feature learning, all you need is data. As long as you have sufficient amount of data, you can try to learn these features from those data points. Now, talking about data, like this is something ImageNet, all of you might have heard. This is a very large scale image classification data set. And this is like something from where this revolution of deep learning started in 2012. Okay, so it has like a lot of categories, different object categories, roughly around 1,000, and there are a lot of images. Earlier there used to be fewer, but it's actually growing day by day. So right now, roughly you have more than 14 million images. And in the testing set, you have around 100,000 images. So if you think about like those classical algorithms, it wasn't even like feasible to think about, I mean, how will you use that many images to maybe do some kind of feature engineering, or how you will like even test all these images. And the reason was the limitation of computation power. Okay, so the idea about learning these features is once we have these lot of samples, we try to learn from this from this data. So now we'll briefly give you like an overview how this learning process is done. And again, this is all high level. We'll go into detail as we move on in deep learning. Okay, so these are just basics. Bear with me. Now, the idea is once you have a large scale data set, what you do is you first split that data into some subsets. So usually 3 subsets. The first one is called training subset. So these are your training images, which means that these are the images which you will use to learn those features. All right. And if you are training, let's say a model, which if it's an image classification problem, you can say that that's a classifier. So these images will be used to train this kind of model. Then the second split is you will have validation images. All right. So validation images are once you have trained your model, then you will try to evaluate that model on these validation images. And then you will see, okay, if the performance is not very good, then you will try to fine tune some of the parameters to improve your model. Okay, so that's the motivation. So you won't train on this data, but you can actually take feedback from this data on how well your model is doing. And if it's doing good, you will keep the parameters. If it's doing bad, you will actually try to improve your model. So this is called also fine-tuning your model or fine-tuning your hyperparameters. Again, we will talk about all those things. Don't have to worry about if you don't understand what a hyperparameter is or what model tuning means. So that's perfectly fine. Okay. Now the third set is, this is important. These are testing images. And when you're training your model or when you're trying to learn your features, you will not touch these images at all. Okay, so these are kind of hidden images. And the labels will be secret. And eventually, when you say that, okay, now I have a perfect model, then you will use that model to just test on these images. And that will tell you how good your model is doing. And ideally what happens is, if these are like, you can say like all the data is 100%, usually you may want to split maybe 60% of the data for training, 20% for validation, or 20% of images for testing. So that's just one way to distribute, but you can have variation. Ideally, you want to keep a lot of samples for training. All right. Now let's try to understand like different learning phases when we are training those models on the training data. So these will be your training images, and you will extract like some kind of features from these images. We'll talk about how to extract those features. Don't worry about that right now. Once you have those features, you will train your model. So that's called model training. And the way you train your model is you need some kind of labels. And that's also called ground truth, which will help you in training your model. So the idea is, let's say you have this image. All right. So you extract the features, you train your model, but right now you don't know how good your model is doing. So for that, you need to know this is an image of Apple. Okay, so that's called image label, and that's also called ground truth. So then what you will do is whatever your network is predicting, you will try to match that with the label or the ground truth, whether you are able to predict Apple or not. All right, so that's why you need labels, and based on how good your model is doing, then you will try to update this network. And once you have finished that process with like the whole data set, you like do a lot of iterations, a lot of rounds of that. And again, don't worry about it. We are going to cover that later in more detail. That's going to give you a trained classifier. All right, so once you have this trained classifier, then you have the testing phase. And right now I'm skipping validation phase, so don't worry about that as well. So we are directly moving to testing phase. During testing, you will take this trained classifier and any image from testing which you have not seen during training. Again, you follow the same process. You extract the features and you take the trained model and use the prediction as your result. Okay, so let's briefly talk about like what these image features are. But whatever these features are, you use the same set of algorithm like both during training as well as testing. So these steps will not change. Okay, so features, you can use raw pixels. And of course, if you're not training your model or you're not learning your models, then we saw that using raw pixels doesn't make any sense. It won't give you like a good learning. All right. But if you're learning features, then ideally using raw features is actually very, very useful. You can use histograms. You can use templates. I think we saw that in lecture 1, where we're trying to match like templates with your sample image. Or you can use different set of local features, which I described like a couple of slides back. And these could be like SIP descriptors. These are different variations. Or you can try to learn these features using raw pixel values. All right. So we will cover like 2 aspects of this. The first one is using local features. So we'll study like how to extract these local features. And the second aspect is how we are going to learn these features. That's like the neural network part of it. All right. So as I said, you need labels to train your model. Now, again, to better understand what these labels mean, let's go a little deeper on that, because labels can vary like depending upon what task you are trying to solve. Okay, let's take this example. For example, this is an image of motorbike. If the task is image classification, right, where you just have to look at this image and say that which object is present. So for that case, when you train your model will make this prediction, right, whether motorcycle is present or not. So to estimate how good that prediction is, you need a ground truth or a label. So for image classification, all you need is a very simple signal or a label which says that whether motorcycle is present in this image or not. So that's called, you can say like image label, all right, or you can just say image label or class label. Okay, so if your model is saying motorcycle is present, and the ground truth also says motorcycle is present, your happy model is happy, it's doing pretty good. But if the network says this is not a motorcycle, but the ground truth says there was a motorcycle, then you say, okay, we are in trouble. The network is not doing good. So do something about it. All right. But what we are going to do, so again, don't worry about it. All that is coming later. Now, if you have to perform object detection, which like one variation is you'll have to draw this kind of bounding box. Right. So in that case, as a ground truth, you will need this kind of bounding box on the image, because your model is going to make predictions and saying that, okay, this is the location where motorbike is present. Then to evaluate like whether your model is correct or not, you will need this label. Okay, so for detection, you need bounding boxes. If you want like fine boundary or pixel-wise segmentation, you might need like this kind of boundary. Or you can also do like very, very fine grained recognition where you are trying to detect, okay, whether this is a motorcycle seat, or it's a wheel, or it's an engine, or it's like a mudguard, something like that. Right? So it's going into more detail. Now you can see that as we are moving away from classification to like a more fine-grained detection task, the annotation effort is increasing. All right. Now let's try to understand like what kind of variations we can have in annotation space. On the right here, you can see this is a image segmentation task. So we need like this pixel-wise localization. So the main point is if you want your network to make this kind of prediction, then you will have to provide this kind of annotation as ground truth as well. So that's your labeling cost. Okay, so that's kind of, you can say like fully supervised method where whatever you are expecting from your network, you provide the ground truth. And as we have seen, like segmentation is like very costly as compared to your classification task. Okay, so that's one variation where whatever your network is predicting, you have the ground truth. And like MS Coco is one example of such a data set. Then we can move away from fully supervised, which is called weakly supervised, where what we do is, even if your network is actually giving you very fine-grained segmentation results, you might not have that in your ground truth. So that's called weakly supervised. So one example could be, let's say you are doing object detection, but as a ground truth, I don't give you bounding boxes. I only give you image level labels. I only say that, okay, a car is present in this image, but don't tell you where exactly it is. So it's kind of weak supervision. And you have like a lot of variations. Again, ImageNet is one. And then unsupervised is you don't have anything. We just have a bunch of images and you have to learn. Okay, so these are different variations. And of course, like as you go towards right, you need more annotation. As you go towards left, you will need like less amount of annotation. And again, this kind of varies, like the definition varies from task to task. I just give an example of one task, but that is kind of, you can generalize to other tasks as well. Okay, so now we have briefly talked about features. We need features to train model. We need labels to train model. And this is the actual training part. And then the question is, what exactly is this model and how exactly we are training this? And I have the rest part of this lecture will cover what this model is. And then I have another lecture which will talk about how we train that model. Okay. So that model you can actually represent as a function. And what exactly is happening? You are sending your images as an argument, or you can say like input to your function. And what that model is trying to do is it's giving you some kind of output. For example, if it's a classification task, it's giving you the class label. Okay. So whatever that model is, it doesn't matter. You can represent that as a function. It will always hold. Okay. If you give like an image of tomato, it's going to give you tomato. Okay. So whatever machine learning framework or whatever model you have, doesn't matter whether it's convolutional neural network, it's recurrent neural network, it's just like a very simple machine MLP. You can say that it's a function which takes some input and predicts some output. Okay, so that's a very generalized form. Now, the question is what this function is that defines your model. And we'll come to that later. Okay, so this X could be your image if you're using pixel level values. This could be features if you're trying to use local features. All right, so this is your, let's say, classifier function. That's the output label. Okay, so the training phase is, as we discussed, like in training set, you have a lot of images and you will have labels for those images. So you can describe your training set as this set here. where x1 to xn is like your set of images, all right? And these could be also features if you are using local features. So, and then for each image, you will have some kind of ground truth or some kind of annotation. Okay, so you need this pair. Now what will happen is, for each image or each feature, you will pass this as input to the function. It will make some prediction, and you will match that prediction to this ground truth. And depending upon how good that match is, then you're going to perform the training. Okay, so that's a high level idea of how the training is being performed. Okay, so the idea is, whatever prediction this network makes, like this one y over here, you try to minimize the gap between this prediction and the actual ground truth. Okay, you want them to be very close, or you want them to be exactly same, which never happens, but that's what you want. And you do that for all the samples. And that's essentially your training. Okay, so if you remember like something from your numerical, like mathematics in your high school, this is kind of optimization. Okay, so you're trying to optimize your model based on what is predicting, and you want that prediction to be very close to the ground truth. Okay, so once that process is done, you have optimized your network, or you have optimized your function, then testing is simply you just send like unseen samples to that function, and it will just make predictions. Okay, so that's a trained model.